Hey everyone, it's Taylor Sparks here, Editor-in-Chief of Integrating Materials and Manufacturing Innovation. I have a new paper to talk about. It's about using the Integrated Computational Materials Engineering, or ICME approach, in a real industry use case, in actual line pipe. Now, this work comes to us from lead author Jerry Gould and co-workers at EWI, Axis Pipe and Tube in Texas. So, what is line pipe? These are pipes that we use to transmit natural gas or oil from one place to another. So obviously it's going to be critical that we don't break. And unfortunately, in the past, there have been instances where these pipes have, burst. Take this news report from 2021 where there was a burst that led to a fire under the ocean. It can be pretty catastrophic. So we would really like to make sure this doesn't happen, which means we need to understand how to make the pipe so that it can't have these leaks in the first place. Well, in this paper, they talk about how they're made. It basically says that a very common way of fabricating these pipes from sheet metal into a tube is through electric resistance welding. And they just sort of briefly describe how it works. Essentially, you bring the sides over, and where they overlap, you pinch it down with these little electrical contacts that apply a force and an electrical current at a high frequency, such that you're passing this electrical current through the material to locally heat it up, and that causes it to weld together. Now, there's a problem in this process. It says here that the molten steel forming at the strip edge has a high solubility of carbon, and that promotes diffusion from the solid into that region, and thereby creating a diffusion region that has been depleted of carbon along the strip edge. And that's just going to be delta ferrite, so it's going to be weaker. It says here that widths of that decarburized bands, they can be 10 to 250 microns, and they have roughly half the hardness of the surrounding material. Here in figure 6, they actually show you what that actually looks like. You can see with the yellow lines as a guide for the eye, the carbon depleted region in the middle where it's diffused to the other edges on the side. And it's not just a softening that's the problem. There's actually a loss of toughness, which is a bit unusual. Normally there's this inverse relationship between hardness and toughness, where if you're going to sacrifice hardness, you oftentimes gain toughness, but that's not the case here. It says that Sharpie impact energies drop an order of magnitude in that region, and therefore they become these preferential crack line paths along that decarburized band. Now, there's lots of theories on why that's happening, but that's not what this paper's about. This paper's about understanding how do we just design our weld to minimize the damage from this. They take an ICME approach. Now, if you're a reader of this journal, you know that that means that they're going to take a bunch of tools that tackle different areas of the process, from modeling properties to process to the final microstructure. Specifically, they model energy transfer from the actual induction process of how it gets heated. They model the heat transfer using Rosenthal equations. They use commercial microstructure prediction software, and they even do diffusion analysis. And they wrap all this up into an easy-to-use app. So here, for example, you see the inputs in a sort of graphical user interface where you could put in the weld conditions, and outcome will be, a measure of the predicted performance using this ICME method. The key finding from this study is really summarized in this figure. On the y-axis, you're seeing the Sharpie impact energy, so that's going to be a proxy for the toughness. The more energy during fracture, the higher the toughness. And on the right, they had this bond line recovery. As they were to anneal this under different conditions or change the welding itself, you can get more of that carbon to go back into that decarburized band region. And they show that when you recover it, you see this dramatic improvement in the toughness. So you're actually able to end up with pipe that is more reliable, less likely to fracture. I think this is an awesome study. I love that it has such a clear use case scenario, and I hope you'll read about it in the latest issue of IMMI.